I'm going to talk about the CellFinder plugin that I've been developing. As a bit of background, CellFinder was originally developed as an integrated software for the analysis of whole brain microscopy images. So typically light sheet imaging in clear tissue or serial 2 photon microscopy of mouse brains typically. And the software does various things like register the brain to atlases, segment out the brain to its different regions. So this image here is a coronal section through a mouse brain and each of the individual colors of the brain regions. And then the next step is also to detect labeled cells throughout the brain from various different kinds of experiments. And these images are often very big. They're a few hundred gigabytes, often up to maybe a terabyte for a single 3D image. And so detecting cells throughout the whole brain in 3D is computationally very expensive. So we developed a method for efficient cell detection in these images, which is a two-step method. The first part is using classical image processing techniques to identify cell-like objects. So what we call cell candidates. These are anything of approximately the right size and shape and intensity to be a cell, which includes all the cells, but also potentially lots of false positives and noise and artifacts. And then each of these cell candidates, so just the small area around the coordinates of each of these cell candidates, is then classified by using a 3D ResNet to classify them as being either cells or artifacts. And this two-step approach means that we can get very accurate results relatively quickly. If we had to feed this whole terabyte of data into a convolutional neural network in 3D, you'd be there for days. But because we're only feeding in very small amounts of data into the network, we can analyze these whole brains kind of in maybe a couple of hours. And this is all very good, but the reason I wanted to build a plugin based on this cell detection algorithm is firstly for ease of use. CellFinder was originally a command line tool, which is very quick and very easy to script, but it's not very intuitive and it's not easy to optimize if you don't know what you're doing, because you can't easily see the effect of changing different parameters. And also we wanted to kind of broaden the scope of this algorithm to different applications. It works well in these neuroscience data sets, but in principle, it could be used for any other kind of 3D cell detection in very large images. So we wanted to separate out this algorithm and make it more widely applicable. So the purpose of the plugin was to implement this efficient 3D cell detection algorithm. It was to implement a method to make it easier to retrain the convolutional neural network for people who are not familiar with machine learning, and also to make it interoperable with other software, because you don't just want to usually find the cells, you usually want to analyze them in some way, to count them or look at their distributions or something like that. And that's where software like Nupari comes in, because people can develop other plugins to deal with the output of CellFinder. So there are three goals for the cohort. The first of which was to separate out this cell detection algorithm from the main software, develop it as a separate isolated Python package, and also implement this as a Nupari plugin. It was to also develop a user-friendly interface to allow people to curate these results, generate training data, and also retrain the classification network. And then lastly, to identify another biological application that could also be, that this algorithm could be useful for. So 3D cell detection in very large images. So not a brain, but something similar that's kind of getting into hundreds of gigavoxels. Number three, I haven't got to yet, but hopefully maybe someone in this meeting has got some good ideas. So I'll go into the demo. It's always risky doing a live demo, but I'll start Nupari. And so I'll load some data. So this is a 2-channel whole mouse brain data set. Hopefully you can all see this. This is the back of the brain, and it's a full 3D data set of a mouse brain, which is about 300 gigabytes or something, I think, which is all loaded lazily from disk using Tally Lambert's plugin, nice and quick, relatively quickly. And if I find somewhere where there are some labeled cells and zoom in, you should hopefully be able to see that scattered throughout the brain, there's various labeled cells. And so the task is to identify these cells, but without picking up any of the other noise. These very large data sets often have lots of noise in them. You can see there's a lot of autofluorescence. You can see the whole brain structure just because brains have a lot of autofluorescence. There's also lots of other bright spots that we don't want to pick up. So there's artifacts on the surface. These are meninges that haven't been removed properly during processing. And there's various other bright spots and things like blood vessels. So that's the aim of the plugin, is to basically just detect these cells. And so CellFinder actually has 3 separate widgets in the plugin. We'll load the cell detection one. And the most important thing is to set the signal channels, because this algorithm works on 2 channels of data, one of which is the signal channel where you can see these cells, where you have your fluorescent label, and the other one is typically an autofluorescence channel, which has similar kind of autofluorescent background signal, but doesn't have these labeled cells. So the idea is that it uses both the size and shape of the cells to classify them, but also the relative intensities in the signal in the background channel. So the voxel size is already set. There's various parameters, most of which don't need to be set. And then I'm going to run this, but I'm just going to run it on this button here. Just runs it on kind of the planes that are local to where you are. So the cell detection algorithm runs in 3D, and it uses the planes kind of in front of or behind the one you're looking at to analyze. So this is just going to run it on, I don't know, I think about 30 or 40 planes in this image, rather than running on the whole data set, because we'd be here for about an hour. It takes a little while because this data's on an external hard drive because I'm on my laptop, but it's done the cell detection step and it's just about to do the classification. It's always dangerous doing things live. I think it's nearly done. One thing obviously I need to add is more visual feedback within the PARI here. We're relying on the console to tell us what's happening. But yeah, it's now done. So you should hopefully be able to see in yellow, it's picked up all of these cells, and you can see that they're highlighted by circles, but they're actually spheres, and you can see that the cells are detected in 3D. And it does a pretty good job. There's probably some mistakes somewhere, but it picks up all of these cells, which are actually kind of hard to see even by eye. And it doesn't pick up anything in the rest. There's no false positives in the rest of the brain. And if we show the rejected points layer, so these are cell-like objects that were picked up by the first step, but have been rejected by the network. And you can see there's lots of bright spots throughout the brain that are not cells which have been initially detected, but then rejected, and lots on the surface of the brain as well. Everything looks fine, but there's usually some mistakes. So the next thing to do is to curate these results. So if I close this widget and open up the curation widget, this allows you to both just manually edit the results, but also to generate new training data. So the training data are just cuboids of data, kind of 50 by 50 by 100 microns, which are centered on these cell candidate positions. So I can add new training data layers, and then I can go in and, in this case, just use the results I already have. And in this case, I'm just going to confirm these as being cells. I will confirm these things as not being cells because they're not even in the brain, and hopefully find a mistake somewhere. I think they're all fine, but I'll just say that this one is incorrect and it's not a cell. And then we save this training data somewhere, and then it will extract the cuboids of the data just from the main image. So you've got kind of a the reusable and portable set of training data without, so you don't need to save all the raw data, and also a YAML file which points you to this. So if I load the last widget, which is the training widget, we choose the YAML file that we've just created, choose an output for where we want our trained model to be created. And then we can do various things. So we can continue training from a previous model. We can choose existing models that ship with the software, or you can just choose your own model. The models that are included at the moment they're all 3D ResNets, and you can choose from any of the 5 from the original paper. And then there's kind of standard options for training convolutional neural networks, so we can do data augmentation, we can run, this is all in Keras and TensorFlow, so we can run TensorBoard to visualize the training and change the epochs and batch size and all that kind of stuff. And I'll leave the demo there because you don't want to watch me train a network for a couple of hours, and go back to the presentation. So, answering these questions that we were given, was anything unexpected or surprising during the cohort process? This should have been an obvious point, but there's a lot more goes into the plugin than you think is needed. I noticed when I use my own software, I don't change a lot of parameters, often because it was kind of designed for my data. And also, when I do change them, I change it very quickly and I don't really think about it. But when you realize actually how much you need to display to the user, and how many parameters need to be exposed to the user, there's a lot more that goes into it than you think. And another obvious point, kind of answering the question, did you learn anything? Again, I know this from just using software myself, but graphical software is used very differently than either command line software or like an importable Python package. In command line software, you can just present the user with all the parameters in a big list and they can pick the ones that they need. But when you're developing graphical software, you need to show the parameters in a logical order, and there needs to be some kind of flow between them. And that's something that needs to be improved, I think, in the plugin as well. Which brings me on to the next thing. So next steps for the plugin. Definitely the user experience needs to be improved. It's a bit clunky at the moment. It's always going to be slow, this software, relatively slow, this software. I mean, it's quite quick that you can analyze hundreds of gigabyte image in like an hour or so, but that's still a long time for graphical software. So I need to improve, especially the feedback, and so the user knows what's going on. It doesn't just quit Napari thinking it's all crashed. And also kind of improve the flow between the different parts of the software. At the moment, everything's implemented in 3 different widgets, and I think I want to kind of bring all the widgets together, probably in different tabs, so you can kind of go easily between them, between the different steps, and also do things like hiding some of the more advanced parameters so that it's a lot simpler and users really know what it is they need to change. And also need to implement other plugins. So I kind of alluded to this earlier, the cell detection is just kind of a small part of a larger software suite for analyzing these big images. So there's other things I want to implement as plugins, so things like registration to standard brain atlases, and then also developing ways of kind of linking all these different plugins together so you can chain them together and do much more complicated analyses rather than just detecting cells. And finally, my hopes for Napari and bioimaging. I mean, I have a lot of hopes for Napari and bioimaging, but the one thing that I'm kind of hoping for immediately is that, well, not immediately, but soon, is that Napari can help kind of facilitate the sharing of training data for all of these many machine learning approaches, and also sharing trained models. There's been lots of good work in this, especially with kind of the bioimage model zoo. But it'd be cool if people, when you're using these plugins in Napari, people can generate training data and then immediately press a button to share it online and fetch other people's training data and fetch trained models to really, really simplify this process, because these tools are pretty much only as good as their trained models. So if you can facilitate that and get people up and running quicker with a more appropriate trained model, then that'd be great.